Hello, everybody. Thank you for joining us today. My name is Ronaldo Pinto. I'm the Technical Sales Director for AFT. My email is ronaldopinto@aft.com. And today I'll be hosting today's webinar where we'll be talking about AFT xStream, AFT new product for steam and gas transient analysis. If during the presentations you have any questions, please type into the chat room or GoToMeeting. And at the end of the session, we'll have a question and answers session where I'll try to answer them. If we don't have time, you'll receive an email with an answer to your questions. Before we start, let's talk about the agenda we'll be covering today. We have an introduction. We'll start with an introduction of gas transient events. Then we'll be talking about xStream, some capabilities. Then we'll move on to why AFT xStream, why you should, how it can help you, typical applications that we have found. Then we'll be covering some aspects of the code compliance and how they address several topics that xStream covers. Then we'll be talking about the difference between fluid and gas waves, pressure waves, and how they travel, and some challenges that AFT faced to release xStream. After that, we'll be talking about an interesting example of relief valve discharging into a header, and then we'll move on to another example talking about steam blowing. Finally, we'll touch pulsation frequency analysis, and we'll be talking about xStream PFA module so you can check according to API 618. The general purpose of this webinar is to give you a general view of xStream. And then in the future, we'll cover some specific topics in another webinar. So pressure transient and pipe necrots get triggered by various events, some of which are accidentals and others form part of operational and safety procedures. When these transients occur, the plant can be out of service for a long time until the root cause is found and an appropriate solution is implemented. Most of the dynamic analysis is done in a corrective manner and not in a preventive manner. Furthermore, these pressure waves may cause large dynamic response on the pipe and large loads on the pipe restraints. The response and vibration on the pipe will depend on the pressure waves amplitude, frequencies, the natural frequencies of and the dynamic characteristic of the pipe itself. Consequently, the design of the piping system must consider the response of these dynamic loads, and so the consequent vibration and stresses can be calculated in order to ascertain the integrity of the pipe. Again, with xStream, you can design in a preventive manner the dynamic loads generated by gas transients and not in a corrective manner where sometimes it's done. What is xStream? xStream is our new product, AFT new product. It's a visual platform for modeling compressible fluid transient and pipe networks. AFT xStream models rapid compressible transient events in gas and steam piping systems. The solver is based on method characteristic similar to the solver used in AFT Impulse. AFT xStream can capture the wave transmission of pressure and flow based on the fluid wave speed and bulk velocity. AFT xStream provides precise results without oversimplifying assumptions like isothermal flow. Solves all the fundamental equation, mass, momentum, and energy. and models real gas effects. So why should you consider using AFT xStream? Transient analysis isn't always intuitive. AFT xStream helps you visualize, understand, and then predict your system response. It will help you ensure your system will function safely and reliably to avoid downtime. It will help you avoid excessive, conservative, and expensive design with improved precision. You will be able to calculate peak-to-peak pressure limits for PD compressors. Pipe stress engineers looking to determine forces from a transient event. It's a good news for AFT users. It complements AFT modeling capabilities for AFT arrow and impulse users by allowing them to model transient event and compressible fluids. So for those AFT arrow and impulse users, the interface is very similar, and it will be easy for them to understand how to use AFT xStream. It rounds out AFT pulsation analysis capabilities by allowing AFT impulse PFA users perform frequency analysis for reciprocating compressors according to API 618. And finally, and very important, it will allow you to comply with codes. Typical applications, and if you have other applications that you can tell us where you find xStream would be useful, please send me an email, and we will consider building an example for them. Pressure drops in pipe forces during steam and gas turbine trips. Steam hammer and gas hammer. Disrupted delivery conditions to equipment, parallel operation, and if one trips off unexpectedly. Turbines, compressors. Pipe forces during relief events. Tank blow down and charging. Time it takes to reach in a specific pressure. Gas pipeline transients. Flow delivery timing, communication time, plants. Instrument air system disruption to distribute devices when one device is activated. Pulsation caused by reciprocating compressors. So now let's talk about how some codes address some of these applications and what suggestions they have regarding. So let's start with API 521, pressure relieving and depressurizing system in the section 4.4.10.2, where it talks about transient pressure surges. In section 4.4.10.2.2, it talks about a steam hammer, and it defines the same. It defines it in the following: an oscillating peak-to-peak pressure called steam hammer can occur in piping that contains compressible fluid. The most common occurrence is generally initiated by rapid valve closure. This oscillated pressure surge occurs in milliseconds with a possible pressure rise in normal operating pressure by many times, resulting in vibration and violent movements of piping and possible rupture of equipment. So this is how API 521 defines steam hammer. It does not give any guidance on how to handle it. Another code that is commonly used is ASME B31.1 power piping. And although it's focused on steam, it's used as a good reference for many pipe stress engineers when they're designing other gas transient events. So in section 5-11.1, it talks about steam hammer. And in section 5-11.2.1, It defines steam hammer. Dynamic loads due to rapid changes in flow condition and fluid state in the steam piping system are generally called steam hammer loads. Piping response to this momentary unbalanced force can be significantly high pressure in steam systems, such as steam, hot and cold reheat system, bypass, and auxiliary steam system that are subject to rapid interruption and establishment of the full steam flow. Then it talks about the responsibility of the designer and the operating company. The operating company should develop procedures to determine any adverse effect of steam hammers, such as excessive pipe movements, damage to hangers and restraints, and high pressure stress and reactions at pipe connections to equipment, where such movements, stresses, and reactions exceed safe limits or allowable loadings, a program of remedial actions should be implemented. So it tells you have to consider transient event to gases and what it calls steam hammer. Continuing with B31.1 on the non-mandatory Appendix 2, rules for design of safety valve installation. This Appendix 2 addresses two types of discharges for relief valve. One is for relieving to atmosphere open system, but in that case, it has a very good guidance on how to calculate the reaction forces. So that's why we're not going to touch them, but still you can use xStream to calculate those reaction forces when a relief valve discharges to the atmosphere. So we'll be addressing with the example section 2-2.3.2 reaction forces with this closed discharge system. And the reason why we're going to I brought this up is because it doesn't give you guidance on how to calculate the dynamic forces. So what does the appendix say? Relief valve discharging into an enclosed piping system, which, and sometimes when it says an enclosed piping system, it refers to a header, create momentary balanced forces which act on a piping system during the first few milliseconds following the valve lift. The pressure waves traveling through the piping system following the rapid opening of a safety valve will cause bending moments in the safety valve discharge piping and throughout the remainder of the piping system. In such case, the designer must, and it's interesting because this is a non-mandatory appendix, but it uses the word must compute the magnitude of the loads and perform an appropriate evaluation of their effects. As you can see, it just warns you and requests you to do the calculation of the wave traveling when the relief valve opens, but it doesn't give you any guidance on how to calculate dynamic forces. Also, we'll continue with B31.1, where it talks about flushing and steam air blowing. And it talks in this section 122 about temporary piping. Why do we talk about temporary piping? The code says the flushing or cleaning operation may be accomplished by blowing out steam or air by hot oil circulation of oil system, by acid or caustic fluid circulation, or by other flushing and cleaning method. Temporary piping, that is piping attached to the permanent piping system whose function is to provide means of introducing and removing the fluids used in the flushing or cleaning operation, shall be designed and constructed to withstand the operating condition during flushing and cleaning. So now that's why we talk about operating a temporary piping system, because it's the one used in steam blowing. And in section C, it refers to what the designer should consider. The temporary system shall be supported such that the forces and moments due to static, dynamic, and expansion loadings will not be transferred in an unacceptable manner to the connected permanent piping system. So you have to design properly when you're doing a steam blowing operation and consider the dynamic loads generated when you open the valve to flush the system. So let's talk about the difference between the waves traveling in liquid and gas. Here we have an animation. This is an animation in liquid, and this is an animation in gas. So when we talk about liquids, liquids are barely compressible. Increasing pressure on water by 200 atm atmosphere will only change the density in 1%. This means we can set a constant wave speed, and that's what you see in AFT impulse. Waves becomes comparatively easy to track. But in gases, what happens? Gases are very compressible. Gas density is strong. It's a strong function of the pressure change. As you can see in the animation, the wave travels, and right in front of the wave, the density increases. This increases the velocity of the wave as it travels through the pipe. All fluid properties can change substantially during a transient. Waves move slower, but have stronger thermal effects. Waves are very difficult to track. So these challenges were faced by AFT to develop AFT xStream. Solving these problems the right way is very computational expensive. Many elements, sections, are sometimes necessary for highly accurate results. Individual computations are harder. More equations, more unknown. Real gas effect versus constant density equations of state and enthalpy models, etc. Some models may take a long time to run. And this is one of the drawbacks of xStream that we're trying to fix. Some models may take hours and even days for some cases. This is because AFT xStream does not take shortcuts. AFT xStream could likely be made to run faster in the future, and we're working hard on that. But like full CFD solvers, there's a minimum very large number of computations that must be solved. So for those AFT users that are used to have a short run times, yeah, xStream will be different in the meantime for first version, and it will take longer to run. Pressure in liquids. So let's talk about wave and fluids in liquid versus gases. Pressure in liquids is typically higher than gases. So it might therefore seem that forces in gas systems are low, but they can be significantly higher under the right circumstances. So here we have two systems. The same model with incompressible impulse, model with impulse, and with compressible fluid model with xStream. In the liquid compressible model by impulse, we get a force of 14,000 pounds. Now the same model by xStream gets 40,000. So sometimes intuitively, you might think that forces in compressible flow might be less, but in some conditions they might be higher, as this example shows. So now let's move on to an example, a relief valve discharging into a header. Here we have three tanks: methane tank, ethane tank, propane tank. They are discharging to a header. The relief valve opens in 0.5 seconds. and we want to calculate the unbalanced forces in the piping, the pipes discharging to the header. We want to calculate the forces in pipe 7. We want to calculate the forces in pipe 8, and we want to calculate the forces in pipe 9. Notice in the model that we're connecting to the header in an angle. The reason for this is that headers in a refinery are designed with a slope, and this is because we want the condensate that's generated when the relief valve opens to flow by gravity to the no-cut drum before it enters the flare. This poses a challenge because the connection shall be of the discharging pipe to the header shall be an angle. So when it opens, it helps the condensate flow and it doesn't interrupt it. This forces the pipe stress engineer to design a support to handle the forces generated, the dynamic forces generated when the relief valve opens. And the reason for this is because high momentums can be generated in the connection, and you want to avoid high stresses in the connection with the header. So just a reminder, we're going to be using SAME B311, Appendix 2, non-mandatory rules for design of safety valve. And it tells you that the pressure wave traveling through the piping system following the rapid opening of the safety valve will cause bending moments in the safety valve discharge piping and throughout the remainder of the piping system. In such case, the designer must compute the magnitude of the loads, perform the appropriate evaluation of their effects. So the code requests you to analyze how the relief valve opens and the effects of the pressure wave traveling when the relief valve opens. So the first thing you should do when you calculate so let me bring AFT xStream. As you can see, it's very similar to AFT Impulse. So your AFT Impulse user or Arrow user will be very familiar with the interface. Here we have the tanks opening, we have the relief valve opening right into the header. We have the event, the transient event, the valve opens in 0.5 seconds totally. And also you can do, this is a time event, you can do also single events, dual event, cyclic, or dual sequential events. So the first thing to define is the force sets. We want to define the force set in pipe 7, which is the one that connects to the relief valve, pipe 8, and pipe 9, which is a pipe that connects to the header. For pipe 7 and pipe 9, we use a differential exit option since each one of them has one elbow. So the momentum created by the dynamic flow is calculated considering one elbow. Here we have the resultant force. So in pipe 7, we have a force of 437 kilograms, which is quite high and might be too high for the relief valve to handle. In pipe 8, which is the next pipe, we have 146 kilograms, which is not so high, so it will help you design the anchor in case you're using the anchor to control the forces that go to the header. And finally, in the connection to the header, we're getting 819 kilogram forces. So the resultant forces, as I said, is 437 kilograms in the connection with the relief valve, 146 kilogram forces in this. So if you're going to use an anchor, or a stop or a guide, you know the forces. And finally, as I said, we have a very high forces in the connection, so you might have a high moment created in the connection to the header, and you might want to reduce the forces created because you might have you might exceed B31.1 code stress in the connection. Knowing the forces, now you can calculate the stresses generated in the pipe, design the supports, avoid high forces and momentums in the relief valve that can cause permanent deformation in the seat of the valve with the consequent leaking, and find a solution in case there's any problem. Like in this case, we saw high forces. We might want to address that problem before we move on to do the stress calculations. And also, knowing the forces, you can comply with code. How do you comply with code? You can export the forces after the magnitude of the forces to a pipe stress program. And here we're exporting to Caesar. You can also export to AutoPipe as well. You can perform an spectrum analysis and time history analysis. Currently, we work a lot with Hexagon people to improve this interface, and as well as Bentley people. And we're going to have a webinar, a future webinar, talking about how to export forces to a pipe stress program and perform either a spectrum analysis or time history analysis for using xStream. So now let's move on to another example. A boiler steam blowing. So here we have a boiler. We have the manual, the valve used to flush the system and clean it. We have the connecting pipes, temporary pipes P16, P17, and P17 discharges to atmosphere. We want, the valve opens in 0.3 seconds, and we want to calculate the imbalance forces in the temporary pipes so we can design the supports accordingly to handle these forces. Again, a reminder of the code that we're going to use. We're going to use a B31.1 power piping, where it refers to flushing and steam blowing in the section 121.10 temporary piping system. And in section C, it tells you, it guides you on what you should do, the type of analysis you should do. The temporary system shall be supported such that forces and momentums due to static, dynamic, and expansion loadings will not be transferred to in an unacceptable manner to the connected permanent piping system. One of the things that's interesting for when you're performing a steam blowing operation is to observe how tank pressure and temperature changes, and how long it takes to, and how it changes in time. So here we have a graph of pressure, how it changes in time. It moves from 14 bars down to 4 bars in 2 seconds, and the temperature goes down from almost 410 degrees Celsius down to 280 degrees Celsius and 2. So this is, you can graph this and you can observe how the operation takes place and how the relief of the boiler happens as time passes and during the blowing, steam blowing. So the same as, let me bring the example in xStream. So here we have the model, we have the boiler, we have the valve that is used to flush the system that perform the steam blowing operation, and here we're discharging to to the atmosphere. So the first thing you do is to find the force sets where you want to calculate the forces. Here, I'm applying it to pipe 1 and pipe 2, pipe 17 that discharges to the atmosphere, and pipe 16, but you can do it for any pipe in the system. The same for pipe 17, we use the differential exit option because it's different. It only has one, it's discharging to the atmosphere, and it has one elbow, so we want to calculate the change of momentum due to the flow, considering it has only one elbow. Here are the resultant forces. We can see how they change in time for pipe 1, pipe 2, pipe 17, and pipe 16. We can see the maximum forces for pipe 1 is 21.17. Pipe 2 is 92.81. And for pipe 17, the one that discharges to atmosphere is 105 kilogram forces. And for pipe 16, the pipe before, pipe 17 is 118. So now we see the system. We can see the loads in pipe 1, pipe 2, pipe 16, and pipe 17. And now we can design the supports to handle these loads. As I said, you can calculate, you can as well ask xStream to calculate the forces for the rest of all the pipes, so you can design the guides and anchors and stop properly to handle the forces generated by the dynamic loads. So knowing the forces, now you can calculate the stress generated in the pipe, design this temporary supports, find a solution in case there's a problem, comply with code requirements. And this is very important because as we know, code compliance is very important when you design a system. The same as the previous example, now we export the forces to a pipe stress program. You can, as the same, you can do a spectrum analysis or time history analysis. In this case, we're exporting to Caesar. And as I said, there has been many improvements. Now you can add the unit vector so Caesar can read it and you don't have to input it for the unit vector for the forces. So now we're moving down to pulsation frequency analysis that you can perform using PFA module. As we know, in reciprocating compressors, pressure pulsation can lead to fatigue, pipe failures, reduce system efficiency, and reduce capacity. One key element to solve a vibration problem is to determine whether the source of high vibration displacement is due to acoustical or mechanical resonance. That's the first thing you have to do to investigate when you do a vibration analysis. Why? Because depending on the source of vibration, the type of solution varies. There's acoustical solution and mechanical solutions. Acoustical solution could be, for example, using an orifice, of using a gas tank. Mechanical solution goes to another. Mechanical solutions are more to improving the quality of your supports. Some supports like U-balls do not constitute a dynamic restraint for the pipe, and that allows the low frequency modes to appear. And as we know, low frequency modes require low energy to be activated, and hence you can see high displacement in the system. Another mechanical solution can be also changing the location of your supports. And why do you, as I said, you have to determine whether you have an acoustical problem or a mechanical problem and use the proper solution. Why? Because if a mechanical solution is applied to an acoustical problem or an acoustical solution is applied to a mechanical problem, it is unlikely the problem will be solved. Pressure pulsation propagates through the piping system at about the speed of sound. Pressure flow pulsations reflect geometrical discontinuities. Wave reflection and interaction results in a system acoustical natural frequency. So each system has acoustical natural frequencies, and it's the ones you want to avoid when you operate your compressor. System will show an acoustical response to an acoustical excitation. Presence of acoustical natural frequencies may result in acoustical resonance. The phenomenon takes place when the return of a reflected pressure wave generated by periodic excitation coincides with the generation of the next pressure pulse. The amplitude of the vibration response can be amplified 2.5 times or higher at a near component natural resonant frequency. So if you're operating near acoustical natural frequency, you will have acoustical resonance, and consequently, you will probably have high displacements on your pipe. The importance of acoustical analysis is reflected in API 618 standard. Acoustical simulation can be employed to calculate the acoustical behavior of the gas in the piping system. With acoustical simulation, the system dynamics can be understood in advance, so the problems caused by pressure pulsation can be minimized or avoided. xStream PFA module pulsation frequency analysis uses a digital simulation technique to model the acoustical behavior of the piping system. What PFA module does is it applies what we call a digital hammer, where internally it hits the pipe and sees what acoustical natural frequency are excited. So here we have an example. We have a compressor, and we went to the and we're discharging at a pressure P, and we want to see the natural frequencies and run a test to see whether or not what response will we get if the compressor operates at one of them. So here we have the response of the in the frequency domain, the peak to peak, the amplitude, and we see that two natural frequencies in pipe 1 are identified as potential critical system. We can see it here at a high and here at a high, at 21 hertz, at 58 hertz. So now, these frequencies can now be used to determine the pressure response of the system caused by pulsation in the compressor and see whether or not if the compressor operates near those frequencies would be compliant with API 16. So now we do the checking of the compressor operation at 29 hertz, as you can see. Here we run the compressor at 29 hertz using PFA module. And here we have the pressure static response at 29 hertz. So here's the response. The maximum is 440 PSI. The peak-to-peak allowable, according to API 618, is 113%, and the resultant actual peak-to-peak percent is 104 and 105%. So this means that if the compressor operates near 29 hertz, it will pass. So you would comply with API 16. The same procedure would need to be applied for 58 hertz, and you would need to comply to see the peak-to-peak allowable for that frequency, and whether or not the actual peak-to-peak percentage complies with the API 680.